Thank you, Donato.
And if you stay more close to the microphones, you will be recorded for a second.
I will try to stay closer. Well, thank you, Donato, for the introduction. I think I picked up a few words of what he said, and some words he might have used in Italian, and I trust that they were all good things. I'm very glad to be here. I understand this is an assembly of the Italian stress analyst group and also the Italian group of fracture. So welcome to both the groups. I have, of course, been in the field of fracture for a long time. I started in 1970, but my interest in fracture and fracture mechanics was actually after taking a course on experimental stress analysis. So the field of experimental stress analysis is also very close to my heart. And all the kinds of things that I do are basically materials oriented, but at the same time, I try to become very conscious of how these materials and material properties that we evaluate are going to be useful in structural integrity analysis. So to me, the field of fracture and stress analysis are very closely connected to each other. And I sort of work on the fringes of both sides, streaming from the very basic material properties up to doing some stress analysis. And of course, I should also say that it's good to be in a country where people can pronounce my name perfectly. I've lived in America for 39 years, and for some reason, Americans have a very hard time with my name. There are words in Ashok, Ashok, but very seldom I see somebody say Ashok, which is how my name is supposed to be pronounced. But when I'm in Italy and when I'm in Germany, they can pronounce my name exactly. Right? So it's nice to be in a place where they can know how to pronounce my name. I've also enjoyed the Italian cuisine for the last couple of days, thanks to Dr. Fidal. So this morning, it was a difficult transition for me from the Italian wine and nice dinner last night to trying to say something technical. What I'm going to do in the next 25 minutes or so to talk about an overview of a topic that I have been working on for some time. And there are lots of collaborators that I need to acknowledge right from the beginning. I will touch upon some of the work that is done by 4 PhD students, Dr. Rahul Rajkarya, Paul Willett, and Shubhra Bansal, and also one undergraduate student, Cody Jackson, and another PhD student, Salvi Ko. All these people have contributed to the work that I'm going to be presenting today, and then I have a few faculty colleagues, Ted Hartwig from Texas A&M University, who made some of the material that I'm going to be presenting the properties from, Doug Spirot from the University of Arkansas, who did some of the molecular dynamic simulations that we are using also to study these material properties. And we have Cody Jackson, who's an undergraduate assistant, research assistant. So we have a very good team of people that we have worked with for several years, and I have the pleasure of presenting the results from those studies. And 4 PhD theses, as I said, have resulted from the work. Now, just to give you a very quick overview, when you take metals and you keep shrinking the grain size, then these materials become stronger and stronger. So what I have here is just a simple stress strain behavior of what I call as microcrystalline copper. Microcrystalline copper will have grain sizes of about 10 to 35 microns, whereas the nanocrystalline copper, which is the top curve, would have the grain size of about 50 to 200 150 nanometers. Okay? Now, the reason why there is such a huge range there is it is very difficult to measure the grain size in the interior. You can use some X-ray techniques, and the X-ray techniques give you a number which is actually smaller than the actual grain size. Then if you measure the grain size on the surface, as the grains come towards the surface, they tend to grow. So you pick the larger grain sizes, and that's why I'm giving you a range of about 50 to 250 nanometers as the average grain size. But you can see that the tensile strength of copper has gone up from something like 90 megapascals to about 430 megapascals. So it's about 4.5 times increase in the strength levels. Also on the strain side, it still has plenty of ductility. You do get necking very quickly, but then you get lots of plastic deformation before the specimen actually fractures. So here we are trying to develop copper as a structural material, and I will give you the reason why it is important as a structural material, without losing its electrical characteristics very significantly. So the applications for what we are talking about are mostly electrical applications. Okay, the electrical applications are what we call as interconnects. So the interconnects are those three pillars that you see on the top right-hand corner of this slide. And these pillars are very small. In fact, the spacing between the pillars can be as little as about 25 micrometers for interconnects of the future. And they are subjected to temperature variation during manufacturing as well as during normal usage. So the temperatures can fluctuate, and as the temperatures can fluctuate, you're all stress analysts, so you know that you can generate thermal stresses that are quite large. So if you take one of these designs and you subject them to different temperature variation as we show in the figure, you're going to see that the stresses can vary quite a bit. Now on the right, I'm going to deal with the right-hand side of this figure first. The right-hand side of the figure is a stress strain diagram as you take this interconnect through one cycle. If you work with copper, you can see that the amount of plastic strain is quite large. And if you work with nanocrystalline copper, the amount of plastic strain is very small. So that is the advantage of going to a nanocrystalline copper compared to a microcrystalline copper for that particular application. As the pitch shrinks or decreases, you will see that the required strengths from copper are going to be larger and larger. So this work was sponsored by the Packaging Research Center at Georgia Tech. And before going to University of Arkansas, I used to be a professor there. And we had this combined project in which we were trying to develop interconnects from copper that were of higher strength. On the left side, we have what we call as these high cycle fatigue properties. And you can see again the difference between copper and the nanocrystalline copper. And the resistance to high cycle fatigue of nanocrystalline copper is much, much larger. So that is the attractiveness of this particular material and the reason for why we have interest in it. Now, other than this engineering interest, we also, as scientists, have a lot of interest in the phenomena. Because if you understand the phenomena, then you can perhaps develop other engineering materials, such as aluminum alloys that are used for aerospace applications, and you can transfer some of these concepts into those materials. Now, the most important aspect of this work is the durability. So, initially it looks very good. The next question that somebody will ask is, what is the durability? Is this material going to continue to perform like it is supposed to during several years of service? So it cannot degrade in properties. And that is where most of our work is actually directed towards the durability. So I look at high cycle fatigue of copper, compare it to even what we call as microcrystalline copper from studies, and we can see that the high cycle fatigue properties are very attractive. So that continues to pique our interest in something like this. Then when you look at low cycle fatigue properties, which is a plot of the total strain as a function of number of cycles to failure, in low cycle fatigue region, we don't get that much of an improvement. In fact, if anything, the nanocrystal material has a slightly lower low cycle fatigue properties compared to its microcrystal part. So it depends on the application whether or not this material continues to be attractive or not. So you can understand that we do have applications in the electronic industry as the primary driving force for this study, but we are also trying to understand the different phenomena. And this material is a fascinating model material for understanding basic phenomena. I think we are perhaps the first ones in the world to do some fatigue crack growth work on nanocrystalline bulk materials. People have done work on thin foils, they have done work on small samples that are very difficult to grab, and the properties that you measure consequently are not reliable. In this case, we were able to make samples that were big enough. They are small in comparison to the normal fracture mechanics tests that we perform in the laboratory, but still fairly reasonable in size, that we are sure of the properties that we get. For example, for nanocrystal copper, we were able to use a width of about 0.72 inches or so that would be about 2 centimeters wide. And that's not a very large specimen, but again, it's not a small micro-sized specimen either. And on the right-hand side, you see a picture of a very small servo-hydraulic test frame that we have used for our studies. We have done some fatigue crack growth work, and what you see here is just the wide range fatigue crack growth behavior for microcrystalline copper. So we take the same nanocrystal material, we grow the grains until they become microcrystalline, and then test them. So that serves as a reference for the properties of the nanocrystal materials. And so here we did 2 tests, we got very repeatable results. So nothing spectacular here other than this is our reference material. Did the same thing with nanocrystal materials, and you can see that there is a lot of repeatability in our tests. So this is good news. When we test about 4 different samples, we get different, we get very similar properties. So our test procedures are validated using these specimens, and then we put them together. The microcrystalline copper results are in the blue, and the nanocrystalline copper materials are the pink. Now you can see that there is very clearly a crossover, and it turns out in the literature, when you look at it, depending on the range of the fatigue crack growth rate, you can make the claim that nanocrystal materials are a lot better, or you can make the claim that the nanocrystal materials are not so good. So depending on the range that you test in, you're going to be able to make very different claims. In the high crack growth rate regime, which is actually of interest in the application that we are talking about, we see clearly that the nanocrystal materials have an advantage. Okay. But in the threshold region or slower crack growth rate region, it is the opposite. Then another concern that we had was the stability, as I said, over a long term, does the material remain the same? I'm not going to talk about the work that we've done on nickel because I'm going to focus on copper, and I didn't know exactly how to get the right-hand side of the figure out of the screen here. So let's focus on the figure on copper, which is at 100 degrees C. So this is temperature is boiling water temperature. And we did simple creep tests at different stress levels, ranging from 225 MPa to about 295 4 MPa. And we were kind of surprised as to how quickly this material was creeping. Normally, copper at 100 degrees C doesn't creep like that. If you take microcrystalline copper, you would have to go to temperatures in excess of 350 C before you will get this type of creep behavior. So that was alarming. That on one hand, you have a very strong material, but with time, you have to be very concerned about its durability and its ability to retain the strength. So we plotted creep curves, and sure enough, we saw a huge difference between the creep curves for nanocrystalline materials, and for sure, we measured secondary creep behavior in the case of nanocrystalline materials. And I've got the nickel nanocrystalline materials were a little bit better because the recrystallization temperature for nanocrystalline materials is higher than that of copper. So we can see that phenomenon. Here also, at 100 degrees C, nickel barely creeps, whereas in the case of nanocrystalline copper, the creep rates are much, much higher. So we looked at the fracture surfaces of these creep samples, and when we look at them, we find that the void size, the creep voids that contribute to the creep rupture behavior, are quite large. So there must be something that happens which tends to grow the grains in the case of nanocrystalline copper while it is creeping. So very clearly we reached the conclusion that the grains are actually growing. So even at 100 degrees centigrade, if the grains grow, the typical semiconductor applications can have temperatures up to about 85 degrees C in normal operation, and they can go even up to about 200 degrees C for short periods of time during manufacturing. So pure nanocrystalline copper would not be able to endure the temperatures, and we would not be able to guarantee the reliability of that material. So then there was a student who studied on the main impediments to durability of nanostructures in copper in this case. So we observed that we have grain growth due to exposure to temperature and time. And we also have what we call a grain boundary sliding, which gives rise to what is called the inverse Hall-Petch relationship. It gives to creep at low temperatures, and it gives to stress-assisted grain rotation and coalescence that actually causes those grain sizes to increase. So it is not just thermally activated, it is both thermal and stress activated. So both the higher temperatures and stress can contribute to the grain growth and to what I would say the lack of durability in these materials. So we came up with this idea that perhaps we ought to use dopants. What do you do with these materials to try to regain their properties or try to maintain their properties under surface conditions? So we use dopants for stabilizing these nanostructures and materials. So the first thing we need is we need an element that has a tendency to naturally segregate to the grain boundaries. Okay, so it should be something that is not soluble in the matrix, but it tends to segregate itself and segregate to the grain boundaries very quickly. So then that element will pin the grain boundary at its point, and we should be able to improve the durability or its resistance to grain growth. So the concentration of dopants should be sufficient to, first of all, effectively pin the grain boundaries to prevent migration and sliding, but not cause loss in grain boundary cohesive strength, leading to low energy intergranular fracture. Okay, so those are the two competing things. If you put too many of these dopants, you're likely to initiate the fracture of the grain boundaries because the cohesive strength of the grain boundary will go down. And something happened to the system here without my doing anything. I guess if I can just get some of this up my computer. I think it's trying to tell me that my time is up.
I did not activate. I didn't put any dopant.
Oh, okay, but you programmed it before. So that is the challenge. research on what would be such an element that would work on copper. There is a third part to it too. When you add outside elements to copper, the electrical resistance can change also. So you have to be very careful to make sure that you do not destroy the electrical properties. So in some ways you can see this is a great research problem. It can give you a lot of job security because you can work on it for a number of years trying to perfect it. That's not the case. You know, we have funding agencies in the United States that have a very small vision. You know, their vision is very small term. So if you tell them that it's going to take you 10 years to solve a problem, they don't give you the money. So you have to solve the problem within that period of time. Okay, so to shrink the time involved in solving the problem, I sought help from people who do molecular dynamics. And I posed a very simple problem to them. I said, take a bicrystal of copper. So you have one grain boundary, and that grain boundary is going to be normal to the axis of the stress. And why don't you dope that with a few atoms of antimony and look at the free energy of the grain boundary itself. Okay? So they did a thought experiment in which they took atoms of different sizes. So basically delta R here is a parameter which is the ratio of the dopant to host atomic radius. So you take the atomic radius of the dopant and the host atom and you take the ratio of that. And one of them was this number like 1.6, which actually happens to be antimony. Because doing my research in what materials will segregate naturally to the grain boundary, I found that antimony has very little solubility in copper, and all the atoms very naturally segregate to the grain boundaries. So what you see is that the grain boundary energy decreases very significantly as you increase the number of dopants per nanometer of the grain boundary length. So this is basically a two-dimensional problem, two grains on either side of the grain boundary. And then you can vary the number of dopants that you introduce at the grain boundary. And through molecular dynamics simulations, we prove that the grain boundary energy reduces significantly, and therefore you would get some stability. We also did experiments with from bicrystals to a number of grains. And this is still a two-dimensional structure now, with an initial microstructure that is looking more and more like the microstructure of real copper. And we doped one of the experiments, the simulations, we put antimony in it, and in the other simulation we did not put antimony. And you can see that B is with antimony, and we subjected it to 800 degrees Kelvin for a short period of time. And you can see that the grain structure is pretty much preserved. But when you do the same thing for copper, which is nanocrystalline, but not doped with antimony, the grain structure begins to get destroyed. So we were very encouraged by these simulations, and we used the simulations to actually determine the ideal amount of antimony that would be needed to pin the grain boundaries. And that, of course, depends on the grain size itself. Because as you have smaller and smaller grain sizes, you have more grain boundary area, and therefore you need more antimony to basically provide the durability. So we used these simulations to actually do some experiments. And that work is continuing at this time at the University of Arkansas. We have the material. We have done some initial stability experiments, and those experiments show that very clearly, if you have even 0.2% atomic concentration of antimony, we are able to actually stabilize our material very significantly. And the next process would be to determine the mechanical properties of those doped nanocrystalline materials. So just to summarize, I would say that we have performed experimental studies that have confirmed that nano-grain-sized copper, and I would say 45 to 250 nanometers, have strengths that are significantly higher than their microcrystalline counterparts. The high cycle fatigue and fatigue crack growth resistance of nanocrystalline copper is also higher than microcrystalline copper in the Paris regime, the high crack growth rate regime. Low cycle fatigue properties of nanocrystal material are lower than microcrystalline copper, but adequate for a large number of applications. Nanocrystalline copper loses its nanostructures when exposed to higher temperatures due to grain growth, resulting in stress-assisted rotation and coalescence, and are susceptible to creep and at much lower temperatures due to the enhanced grain boundary sliding. So effective approaches must be found to improve durability of nanostructures, and if you're not able to identify those effective approaches, we will not be able to use copper in that way. So lots of work needs to be done. There are some parameters that the electrical engineers can play with. For example, the height of those pillars is very important. And if they can go to higher strength materials, they can reduce the height of those pillars. So it's not, even if the resistivity of the copper goes up a little bit, you can still maintain the same resistance by actually playing a little bit with the height of those pillars. There's also another factor, which is how do you make these things? In our studies, because we wanted to study the bulk materials, we did that by equichannel angular extrusion, which is a process that Ted Hartwig at Texas A&M has championed. So I don't think you can make electrical components by ECAE process. So you have to find some kind of an electrochemical process to produce those nanostructures. Then the question comes up is that if you take ECAE, nanocrystalline material, compare them to the properties of electrochemical process, nanocrystalline material, would there be a one-on-one comparison? So, as I said, we do have job security for some time, and we can keep studying this. But I think the part that I did not touch with here is the scientific part. And our group has done tremendous amount of work in being able to determine the fatigue properties without doing any experiment. We have computer codes where we can actually subject a very small pillar, very small specimen to fatigue loading, and look at the nucleation of dislocations and how those dislocations can coalesce and form a crack, and how the crack continues to grow. So the scientific value of the work, I can absolutely be very confident that you've learned a lot of things. The usage side, depending on the patience of our sponsors, we can get to that point or not. So being an academic, I guess the science comes first. The use is important, and it's getting more and more important as you go into the future. So we have to be very mindful of being able to solve the problems before our sponsors lose their patience. So thank you very much for your attention, and I would be very pleased to answer any questions that you have for me. Thank you.